Yeah, so this kind of paths are going to give you, RC. So how to avoid such kind of things? By the way, I forgot to tell you, uh, if you have uh, such kind of signals, you may experience something like this. Yes. Or you must have experienced such kind of things, right? Earlier. This effect is known as crosstalk. They're talking to each other, or they are coupled with each other. All these things are synonyms. Any one of them I can tell you, and all are because of parasitic effects of the capacitance. But if they are at DC, it's not going to be coupled, because at DC this capacitor is open circuit, right? So do you have any solution for this? Still we are at 18th century, so we need to come to like 2019. What do you think? Do you have any solution?
Yeah, these are just bare wires or
Just
insulated?
wires, yeah.
Bare.
Bare wires. Earlier we don't have something like probes and all, right? That is what I'm saying.
You can insulate
Yeah, how?
silent
Hmm?
capacitors बढ़ा दो.
So you are saying that I can keep them away from each other.
Either increase the epsilon like
But look, when it goes to oscilloscope, those two channels are, that actually distance is fixed.
what material we will have
Hmm?
over the key this wire.
Can you have some better solution than this one? This is
So
still crude. Look.
we can keep something.
Yeah, so something, what something? What something will help you? Or what something is available everywhere?
Top.
Hmm? Okay, I'll ask. Do you know, uh, you heard about, there is from Paris to London, there is a train, you know, under the sea, you can go there, you heard about this? So within like 2 hours you can reach there. It's but earlier time, when like Graham Bell was making this telephone, at that time what he wanted to make a call from Paris to London, sorry, London to Paris is what he wanted to do. And what he has done, he sent like beneath of the ocean, he sent plus signal and minus signal also. Minus is actually ground. This is what he did. And afterwards, because of this digging up all these things, they made train in that path. But they made this just to make a call, telephone call. They did this. And afterwards, in 19th century, we invented that ground was available everywhere, so it was lots of wastage of money. Can you imagine? Like, it's like London to Paris might be 1,000 kilometers beneath of ocean. So that something is available everywhere is ground or earthing, right? That is what you are saying. So where do you want me to connect that something? You give me solution that if I do such thing, will it work? Or because there might be other wire also, this side or this side also, right? So if I do such, this will work.
Working of grounding.
Yes, right. So afterwards, this has been made in a better way and known as the probe, right, which has BNC connector. So BNC connector has like signal is here, and all the steel part which you are seeing, it's ground, and it's connected to your instrument ground or the chassis of entire instrument. So it's also ground. If you are not connecting crocodile, the zero crocodile to here, still it will work, right? One ground is sufficient to make your circuit in a proper way, right? So this was the first invention in 19th century, that people made probes. But still, like, people are making some small size, big size probes, and it will have different resistance or might be different capacitance. So for the standard, what we have done, let's make following kind of probes: 1x, 10x, 100x, right? So if it is more, it's good, because like 10x probe has around 10 mega ohm in shunt with 10 picofarad, right? Is it correct, right? You can see this thing on your probe itself when you are going to do the experiment. The gray colored probes are available, which has 10 is to 1 and something like 15 mega ohm in shunt with some like 9.2 picofarad, that is written. So it's difficult to make exactly this number, so it's around that number will be treated as 10 is to 1 or 10x probe. When you are using 10x probe, you have to keep every settings of oscilloscope, function generator, everything has to be at 10x. Everything has to be at 10x, otherwise you will get some faulty result. If this is 10x and your oscilloscope is 1x, then your output will be like you are expecting 5 volt, but you are going to see 50 volt, right? But it's a wrong, it's illusion. Okay, this was just for your information. So everywhere it will be RC circuit. We are not going to like talk about generally inductor, because inductor takes more area than capacitor. So all these theory leads to chip designing, where we want to keep everything.
RNC or
Yes,
X is of grounding, like 10
yes, with respect to it's R and C, so they model it like this: R and C. So effective resistance and capacitance is 10 mega ohm, 10 picofarad. If I am going to look from here, so Thevenin equivalent impedance inside the probe is that much. From this side, again it's that much, right? So that's why, like, if it is 1x probe, it's available in 100 rupees in Chandni Chowk. 10x probe, almost 5,000. 100x probe goes to 50,000 or 1 lakh. So I like 10 raised to 5x is around of something like 20-30 lakhs. This is also one of the business people are doing. Okay. Right? If you can design a good probe, that is also a good company. Right? Okay. Okay. So we were here and talking about this. So I was talking about h of s equal to 1 by s plus 1. I believe everybody are expert of complex number, right? There is no doubt. So I'm replacing this Laplace operator with 1 by j omega plus 1. Please follow the mathematics, then and then you will understand. You have to write down. So can you tell me what is mode of h of j omega? Yes, gentlemen, last. Yeah, what's your name? Okay, so Ritik, tell me what's mode of h of j omega for this one. Yeah, 1 plus 1 plus omega square. That's wrong, right? Okay, under root where? The whole thing, right? Or you can write down omega square plus 1 raised to minus 1 by 2. Both are same, right? Now as I wanted to plot decibel with respect to frequency, which is omega, what is going to happen if omega square is much lower than 1? 0, right? So okay, one more thing I need to write: 20 log mod of h of j omega with 10 base is going to give you what? Tell me in decibel. Hmm? Yes. Okay. Yeah. Tell me. Can you tell me the equation? Okay. Minus 10 log. So I am not talking about this one. In general equation. 1 plus omega square. right? So if omega square is much lesser than 1, then this equation is equal to 10 log 1. So how much dB? 0 dB. I'm going to see 0 dB, right? But what if omega square is much higher than 1 in decibel? So you can use this equation and let me know. Minus
20 log
minus 20 log omega with 10 base in decibel. So unit of this one is decibel, right? Sorry. Yeah, base is always 10. That's why it's decibel, right? That is the agreement, because Graham Bell told, so we are following him, right? But what if omega is equal to 1? Because that is also the frequency, right? Hmm? 3 decibel. But 3 or minus 3? Both have different number, right? So minus 3 dB. Very good. Let's try to draw this one. On So all these numbers are with you. If I am interested in drawing omega versus decibel, which has, this is 20 decibel, 40 decibel, 60, 80, and so on. This side minus 20, minus 40, and this side. So this is a omega in log scale generally. So it's log scale. In log scale, you are not going to find anywhere 0, by the way, right? That is known to you, because there is no 0. So you can have some milli microhertz. You can go as small as possible, but you cannot reach 0 ever, right? So let's assume that 1 is here, 10 is here, 100 is here, and this side it will be zero point 0.1. Still this scale is log scale, and I'm not drawing those lines, but next time, maybe from Monday, I'll ask Vivek to get some log paper for you, right? Then we will draw it on log scale. So it will be a tutorial. This Monday, Tuesday is just tutorial, right? So what we found out, when omega square is much lesser than 1, omega square is much greater than 1, and exactly at this point, right? At 1, what is happening? It's minus 3 dB. That is what we found out. So let's assume that this is minus 3 dB. Okay. Omega square is much lower than 1, then you are going to see 0. This is 0 dB line. Yes. And afterwards, in yeah, yeah, omega, but sorry, I should say plotted in log scale. Yeah, but still it's omega. Sorry. Okay, so but you are agree with this one till now? So omega square is much lower than 1, then it's 0 dB. So I made 0 dB. Yes, Divya. Okay. And at 1, it's minus 3 dB. Omega square is much greater than 1, then it's minus 20 log omega. So let's keep the value when omega equal to, okay, it was omega or omega? Omega. So what is happening at 10? Minus 20, right? At omega, it's minus 20. I kept this point here. Now what is happening at 100? Minus 40. Or you can say that with the minus 20 slope, you can draw the line, right? Let's assume that this is 3, right? So this particular line is going to give you the slope of minus 20 dB per decade, right? Yes. Yeah. Any doubt? Okay. Similarly, you can find out. So this question I am keeping to you people. You have to tell me how much dB per octave you are going to see. How much dB per octave? Not 100. It will be lower than minus 20 for sure, right? Lower value will be there, right? You can keep the value 20 here. What is going to happen? 20 log 20, how much? Log 20, how much? Hmm. 26. 26 dB. Excellent. But it's minus. Okay. So with minus 26 dB, can you tell me what is the slope by y2 minus y1 divided by x2 minus x1, right? Minus 6 dB per octave. So in our whole electronics theory, like 6 dB per octave is equal to minus 20 dB per decade. You are going to see such things mainly in communication engineering. They are going to use uh, such units, and maybe the derivation is here. This is the derivation for 6 dB per octave is equal to minus 20 dB per decade, right? So all good till now. So any system which is like this is follow this kind of line, and minus 3 dB is the actually point where this performance is getting degraded. Till that time V out equal to V in. 0 dB is equal to V out equal to V in. It's a good transmission, but afterwards it's decaying, right? So this is known as bandwidth of the system, but this bandwidth is measured at minus 3 dB. That's why this is also known as minus 3 dB bandwidth, right? So there is no problem now. Now let's look at the problem. So this is already drawn by. By the way, still this is also available on like the that what I called material, learning material, something like that. So you can read that. Right? That might be the case that if instead of this, if it is s plus 1, only that much system is available. Transfer function is equal to s plus 1. Then what kind of magnitude response you are going to see? Hmm? So you can write down h of j omega, which is equal to omega square plus 1. So it's minus 10 log omega square plus 1. At much lower value, when omega square is much lower than 1, and when omega square is much greater than 1, and what is happening exactly at 1? So, oh, sorry. Yeah, thank you. Right. Yes, Aishwarya, right? Aishwarya, okay. So you're saying something. So what is happening at omega square is much lower than 1? Why 40? Okay. Okay, so I can write down this one as omega square plus 1 raised to 1 by 2. Yes? No, it happens. It's not. Right? So 20 log will make it plus 10 log. Right? No problem. Now, what is happening at omega square much lower than 1? 0 dB. And what is happening at 1? Plus 3 dB. And afterwards, at 10, 20, 100, 40, or you can say that the slope of this one is plus 20 dB per decade, or plus 6 dB per octave. Yeah. From this we can also see that uh, every system will look like RC. Every system. let's assume that I am talking about the probe, which has such kind of setup in total, where this is, let's say, some 50 ohm, 10 mega in shunt with 10 picofarad. So can you find out its 3 dB bandwidth for this system, where this is V in and this is V out? You might be asked that I want to draw the frequency response or AC response or magnitude response. All have same answer, this one. But you have to change these values, numbers will be changed. It will be changed by the setup, right? Right. So can you find out, right? Can you, so let's keep this one as home task, right? You can do it at your hostel, and you can discuss among yourself. So this number will be changed, and this number will change means it will tell you what frequency you can operate your probe, which has such values, right? So if it will tell you that if it is 1 megahertz, means beyond 1 megahertz, if you are using something, it will not work. Sometimes we are doing this, right? We are giving more value and that probe does not have capacity. When I'm saying capacity, means the bandwidth, and I'm more interested in 3 dB bandwidth, right? Because afterwards it's getting down, right? So any doubt in this, these two plots? If no, then I can go to the next thing. If it is multipole system, is it going fast or all well, right? Okay. If it is multipole, multipole means some r number of poles are available, right? It has r number of poles at same place, minus a, only minus a, right? So what kind of frequency response you are going to see? Can you draw that in your notebook? Answer is already available, I can do it also, but let's think about it. Because hmm? Slope will change, of course. What's your name, by the way? Hmm? Manas. So Manas, you are saying something. Yeah. What was that? Slope will change. Okay. So you are saying that the nature of the plot will be similar, but the slope will be changed. Is it correct? So you are saying that if it is s plus a only, just one, then it's minus 20 dB per decade or minus 6 dB per octave. But in case of r number of poles at a or at minus a, the slope will change. So how much slope will change? Minus 20 times r dB per octave. So if these number of poles are 3, it's minus 60 dB per decade. If 8, minus 160 dB per octave decade, right? And so on, right? Okay. So the solution says like this, as you are saying, it's minus 20 r times log 10 omega, and the 3 dB correction will change to minus 3 times r dB, right? So this is what you are going to see, and okay, right? Now moving towards one of the question asked by, okay, who is, what's your name, by the way? Sorry, I forgot. Devanshu, you asked me one question, I'm moving toward that answer. So let's assume that I am having a system which has multiple zeros, multiple poles, or maybe some gain also, a. But as I asked you in the surprise quiz, the small signal gain or DC gain is equal to a by z divided by p, not a, right? That was the thing. So let's look at that, how it happens. If there is a system which has gain a, 0 and pole, so I can write down in terms of dB. Okay, Okay, it's written in already Laplace. So 20 log a plus 20 log s plus z plus 20 log 1 by s plus p, right? So it's in division. If you want to keep it on top, you can make it minus 20, right? Just with this system which has a pole, we learn three things. At p frequency, this is equal to minus 3 dB. At omega is much lower than p, 0 dB. Omega is much higher than p, it's with the slope of minus 20 dB per decade, right? And for the case of 0, at 0 frequency it's minus 3 plus 3 dB. At exactly much higher than, oh sorry, much lower than z is going to give you 0 dB. Much higher than z is going to give you plus 20 dB per decade of slope, right? And this guy is always same, plus 20 log, right? So plus 20 log, right? So this is what going to happen. So now let's look at the, so this is the real equation which has a equal to 10, z equal to 100 and p equal to 1. So 0 is at minus 100, pole at minus 1, and some gain which is 10. So this gain is not equal to small signal gain, right? So at the end we are going to add all of them. What exactly we are doing in adding all of them is like this. Let's look at the first part, which was 20 log 10 is going to give you 20 dB for all frequency. Going from 0 to infinity frequency, just read x-axis as frequency. Right? This is copied from what I kept it on Moodle, right? So they missed all these numbers. So 0 to infinity frequency. This is x-axis is frequency, y-axis is decibel. So it's plus 20 decibel always for any frequency. Now if I have minus 1, which is availability of pole, so at 1 it's around minus 3 dB, lower than value 1 0, higher than 0 it's minus 20 dB per decade. Similarly for 0 it's s plus 100. So at 0, when you are going to write the equation, it's omega square plus 100 and square root is 1 by 2, right? So at omega equal to, or omega square much lower than 100, what is going to happen? Not 0,
It would be 100 square.
100 square, yeah, because of 1 I forgot.
40.
Yeah. 40 dB, right? So that is what we kept it here, 40 dB. Afterwards, exactly at omega square equal to 100, it's plus 3 dB or some value, right? Plus 3 dB. That's what you can keep it here. And what is going to happen if omega square is much greater than 100? Plus 20 dB per decade. You can check that. Do you want me to derive it or it's fine, right? So you agree with all three plots? This has been modified because of this 0 is available at 100, right? And when I'm adding all of them together at 0 frequency, I'm not going to see just 20 dB. When I'm going to add all of them at 0 frequency, I'm going to see 60 dB. That is exactly what we were claiming at the beginning. Okay. We were claiming at the beginning that let's keep this 100 outside, and whatever is availability of gain, we are going to call that one a small signal, not just 10 a small signal, right? That was your question, right? So this kind of form is known as time constant form. We don't write in terms of normal Laplace operator form, but we are going to write it in terms of time constant form. And time constant form says that please write in terms of tau 1s plus 1, tau 2s plus 1, and so on, divided by, let's say, tau 3s plus 1, tau 4s plus 1. So every time there will be plus 1 will be there at another side, so that at zero frequency you are going to see total of everything. That's why we are defining small signal model as like taking everything out, right? So any doubt for this now? So in total it will look like this one. At omega equal to 1, actually it's 3 dB, and you have to add everything. So it will look like something like this. So in reality it will look like this one. The dashed line which you are seeing, that is what Bode told, that do not make this 3 dB and all these things. We are going to work with the approximation. There is no 3 dB at omega equal to 1. Let's extend the line after omega equal to 1, make the sharp line one more. There is nothing like this is like 3 dB or something. So in Bode plot you won't see 3 dB. So till now it was magnitude response, but by making all this observation he made some plot. But that plot is combination of magnitude as well as phase, and adding these two we are going to tell something which is stability. We are going to predict stability. This is what our role is. Bode plot will only tell me what stability of the system is, whether the system is stable, unstable, right? Do you want to ask something on this? Because starting something new is not good idea now, right?
Yeah. The
Hmm.
last graph.
Last graph, okay.
Yeah, this is increasing.
Yeah, so it's zero. It's zero. Zero is on numerator side. So there is nothing like minus 1 by 2. It's plus 1 by 2. So Divanshu, hmm, this plot, right? We talked about this plot. So instead of s plus 1, it's s plus 100. So this starts from 40 dB and then keep on going.
So when we add them together, so it should increase afterwards, no?
Okay. Yeah, good question. So the thing is, it's minus 20 dB this side, and this is plus 20 dB. So in total, it's 0 dB per decade. Okay. So thank you for asking this question. I forgot to mention this. So, hmm,
If that equation, if we multiply some constant, then what will happen? It will shift upwards. Means
yes, yes,
the graph will shift upwards
yes,
with the value of log 10
locked.
or the
Yes, because it's multiplication is addition in log, so it goes up, right? If you are multiply with 6, it's 20 log 6,
scale.
right? It's just a scale. It's going up. But these things has to be on your fingertip. This is a thing which is very much useful. Maybe already you learned Bode plot. I don't know. Was that same or different?
Yeah, it's
Same, right? Okay. So you can help me for sure. In semilog paper you did it for your project.
yeah. But I use some tricks like first of all.
So that trick is going to be taught on Thursday. So I was deriving all this for you people so that like you should know all the derivation. I'm not here just to give all the tricks only, right? Right. So those tricks are available on Thursday's lecture. So when I'm teaching any higher course, then again I'm teaching that trick. When I was teaching to Himanshu for CMOS analog IC design, So I was starting with those tricks. There is no derivation. I was telling that at DC this is going to happen, at pole this is going to happen. So we made some agreement that whenever I am going to see some pole, it's minus 20 dB per decade, right? So those techniques I am going to write down there, and we are going to use it. We already derived it, right? So this is happening. If there are two poles, it's plus 40 dB per decade. Three poles, 60 dB per decade. Right? Okay. Okay, fine. Then that's all for today. Okay. Thank you.